Okay, we'll go ahead and get started with this video. This video is for Stat360 handout number 11, Part B, and includes pages 12 through 24. Okay, let's go ahead and get started then. We will again be using the impact crater dataset, which is available in the Google folder for handout 11. So, handout 11 Part B is going to include an indicator variable that has more than two levels. So we're once again going to work with the impact crater dataset. Model 3 setup here. So model 1 and 2 were from handout A. Let's talk about model 3. We are going to be using the response variable diameter. The predictor variables are going to be height and projectile type. But here the projectile type has three groups: glass, steel, and wood. Here's what a scatter plot looks like that I obtained in JUMP. We can see that the green here is the steel balls, and they tend to be higher in diameter or cause a larger crater than the other two here. The wood balls that they were using were fairly light, so they did not cause that big of a crater when they were dropped. So before going much further here, I just want to introduce this syntax for model building or for model fitting. This syntax is used in R, and it's more generally an easier way to talk about what you are doing with your model, especially as the models get more complicated. So this is just kind of a shorthand notation for this model. We have the response and then the tilde. We have on the right-hand side of the tilde, we have all of the variables or terms that we want to put in our model. So height is one of them, projectile type is one, and then I want to allow the effect of height to vary across the projectile types, so I want that interaction term in there. So this is how you would fit that model inside of JUMP. I would go underneath Analyze, Fit Model, and then I would place diameter in the Y response box again. The model effects are going to be height, projectile type, and then the interaction term. So this shorthand syntax that I was just talking about is what that looks like in the Construct Model Effects box. Also, if you use software packages like R uses a syntax very similar to that. The other thing, I have deselected or unchecked center polynomials from the red drop-down button here. So here's what that model output looks like. We have a summary of fit. Provides me my R squared here. My R squared is very high, at least relative to what I was getting when I was using sand type in the model. My R squared now is almost 90%, 88.5%, which again just suggests that the amount of variation in diameter that can be explained by height, projectile type, and their interaction. Again, that's a proportion. If that thing is close to 100 or 1, then I've explained all of the variation. The root mean square error here is about 0.6, and that's fairly small given that the measurements, again, the responses tend to vary from about 3 to 11 or so. So that's a fairly small residual value there of 0.594. The overall test is significant. That just means I got some sort of impact going on due to height and/or the projectile type. We also get a bunch of probability bigger than t p-values here that we will talk through next. So when we're looking at the parameter estimates, we can see that we have a projectile type glass ball. We also have a projectile type steel ball. So what the software had to do here is actually create two different indicator variables. So if you have 3 levels, which we have here, software has to create 2 indicator variables. It does not need 3, but it needs 2. So let's talk through that and understand why that's the case. So when my predictor has 3 levels, I need 2 indicator terms. Projectile type glass ball is going to be a 1 and 0, 1 if it's glass and 0 otherwise. Projectile type steel ball is going to be a 1 and 0, 1 if it's steel and 0 otherwise. Now if I want to identify projectile type wooden ball, what I would have is I would have my glass ball set to 0 and my steel ball set to 0. So when both of these are set to 0, then that's going to identify the third type of ball. So I do not need 3 indicator variables here, I only need 2. So let's talk a little bit about the model, or the form of that model. The form of the model is going to look like the following. Has a y-intercept and slope. And this here, the beta 0 plus beta 1 height, is going to be the y-intercept and slope for the wood ball. So recall, wood is going to have 0 for projectile type glass, and it's going to have 0 for projectile type steel. So all of these terms here are going to go away when I'm talking about the wood ball. If I plug in 1 here for the glass ball, so if I'm interested in a glass ball, I'm going to have to plug 1 in here for this projectile type glass ball, and I'm going to have to plug a 1 in here. And in fact, I wrote out all 3 models here on the next page, on page 16. So for a glass ball, again at 1 right there, the beta 2 coefficient, or the term that is associated with beta 2, is projectile type glass ball. And if I'm talking about a glass ball, then that's going to be set to 1. Likewise, I'm going to have projectile type glass ball set to 1 over here as well, so I'm going to end up with a beta 4 times height. So that's what we get here. The beta 3 coefficient and the beta 5 coefficient are not going to show up because those are for the steel ball. And when I'm talking about the glass, the steel ball coefficient is set to 0 here. So I end up with beta 0 plus beta 2 is my y-intercept, and a beta 1 plus beta 4 is my slope. Likewise for steel ball, I just need to be careful where I identify the 0s and 1s, but I'm going to be picking up a beta 3 here for the y-intercept and a beta 5 for the slope when I'm talking about steel. This here should be wood ball. Sorry about that typo. But for the wood ball, the steel indicator variable is going to be set to 0, and the glass indicator variable is going to be set to 0. So all of this stuff, as I said a moment ago, just disappears, and I end up with just beta 0 plus beta 1 time height. So I can use these coefficients now, this list of estimates here, parameter estimates for my parameters. I could write out all of the different regression models, and I do that here on page 17. So just carefully going through, picking up the right coefficients, doing the algebra, you end up getting these 3 regression models. We can see that the wood ball has the lowest y-intercept, and its slope is also the flattest at 0.0137. The middle here is the glass balls. It has a slightly larger y-intercept and a slightly larger slope as well. The steel balls, which are the heaviest, have quite a large increase in the y-intercept. So over a 1 unit increase here from the wood balls. And also the slope increased substantially. The amount of that increase here is identified by that beta 5 term. Let's talk quickly about what these tests mean. So this is on page 18 here. We got a lot of tests. So test 1 is just going to be the y-intercept for projectile type wood ball. Is that equal to 0 or not? Again, that first y-intercept test is probably not meaningful in practice. The second one is indeed meaningful because that second test is identifying whether or not height has an effect on the diameter. So the beta 1 there is the slope. And that's going to appear in all three models up here. So the beta 1 is going to appear in the glass ball, beta 1 appears here in the steel balls, and beta 1 appears certainly in the wood balls. So when we're doing that test, we're actually looking at whether or not the height has an influence on the diameter across all three types of balls. Test number 3 is just determining whether or not I got a difference in the y-intercept between glass and wood. Remember, this is going back to the base setting, glass versus wood here. This projectile type glass ball times height, that would be checking whether or not the slopes between the glass ball and the wood is different from one another. So test 5 here is testing whether or not the slopes are different between those two types. Test 5 is not significant. Test 3 is not significant. And 3 and 5 have to deal with the glass ball versus the wood ball. So it does not appear that I have a difference between those. Test 4 and test 6 would be comparing the steel ball against the wood ball, and those are significant. So it would appear that I would have differences between those. Here what I've done is actually done a custom test of glass versus wood. So this is kind of looking at 3 versus 5. Now these tests, 3 and 5, are doing these individually. I mean, 3 is for the y-intercept and 5 is for the slope. A custom test would allow me to look at those collectively or kind of together. So if I look at my scatter plot here, a test between glass and wood would just be determining whether or not these two regression models are different from one another. How I would set that up is, again, going underneath estimates, custom test. I would need to pick up this would be the beta 2 term, which is glass ball. And this one here would be the beta 4 term, which is that glass ball times height. I want to pick up those terms using a 1 here and then setting those equal to 0 and 0. The p-value is not less than 0.05 down here, so that means I do not have differences between these two types of balls. When I compare the wood ball to the steel ball, again I want to pick up, because I'm doing steel here, I want to pick up beta 3 and beta 5 and set those equal to 0. This p-value is highly significant, so I definitely got a difference in the effect between steel and wood here. So those two lines are definitely different than one another. Now the test between glass and steel takes a little bit more effort because I'm not comparing it against kind of the base setting here. So on page 20, I kind of walk through how to get a comparison between glass and steel. So if you recall, the y-intercept for the glass was beta 0 plus beta 2. The y-intercept for the steel ball was beta 0 plus beta 3. If I want to look at how different they are, I would just subtract those two quantities, and I end up with beta 2 minus beta 3. So I need a plus 1 for the coefficient on beta 2 and a minus 1 for the coefficient on beta 3. I also want to test the slopes. Likewise, I'm going to end up with beta 4 minus beta 5 here. So I'm going to be using plus 1 and minus 1 as my coefficients here. Again, if there was no difference between these two, then this quantity would be equal to 0. So I'm setting that equal to 0, and also this quantity would be equal to 0. The p-value here is indeed significant. So I have statistical differences between the effect of the glass and steel balls. So there's a difference there between the green and red lines. Okay, some final thoughts then regarding Model 3. Test number 2 suggests that height has an effect on the diameter. Okay, so that's kind of an easy one there if we go in, dive in on just the height. So we certainly can say that height has an effect on the diameter. We learned that there were differences between the glass and the steel balls, and we learned that there were differences between the wood and the steel balls. However, we did not have differences between glass and wood. Looking at the residual plot from this model number 3, we can see that we have pretty good scatter there. It looks like a little bit of a hook there with the blue, which would be the wood balls. We might want to investigate that a little bit further. But we certainly don't have those 3 clumps of points like we had in the residual plot from model number 2 that we looked at in Part A. All right, let's real quickly look at model number 4. And this is where you're going to earn your money. So as an applied statistician or a data scientist, you are going to earn a lot of money upon graduation. So here what I'm doing is looking at more than one indicator term. So I'm going to put an indicator term in the model with respect to projectile type. So this is the model 3 here. And then what I'm going to add to it is an effect for sand type. And then I'm going to do a sand type times height, so that's going to be the interaction. And then I'm going to allow for an interaction term between sand type and projectile type. Now this model is going to get quite large and in fact has 12 different parameters in it. Takes a little bit to kind of keep track of what's going on. How would I fit this model inside of JUMP? I would just keep dumping more terms down here in the construct model effects box. Height, projectile type, and then I got the interaction. I got sand type in here. I got the sand type, projectile type interaction. And then I got the interaction with height as well. So I have 1, 2, 3, 4, 5, 6, 7 different terms or variables going into my model. Should be 7 different variables going into my model, which actually produced a total of 11 different terms. And if you count the y-intercept, there's 12 parameters that need to be estimated. Here's the output from model number 4. So this is the model that I just fit up above. My R-squared went from about 88.5% up to 95%. So I am gaining a little bit on my R-squared by including sand type. Talk more about that at the bottom here at the end. So here's all 12 of my different parameter estimates, all the different p-values. If we just kind of keep a high perspective on this, the base setting in this model is going to be wood ball and fine sand. And I know that because it's not showing up in any of these other terms. The way JUMP decides on the base setting is it actually does it alphabetically. So for sand type, I have coarse and fine. It's going to set the coarse to be 1, and it's going to set the fine to be 0, because C comes before F in the alphabet. The wood ball is set for projectile type indicator. The wood ball was set to 0 because it comes last in the alphabet compared to glass, steel, and wood. So that's how JUMP does that. You can change that by just reordering the effects if you want in JUMP. So you can change the order in which they are displayed. Notice that most of the p-values that deal with the steel ball, another typo there, most of them that deal with the steel ball are significant. Okay. If you look at the sand type coarse height here, That's determining whether or not I need a different slope for the different sand types, and it does not. That was what we saw in Handout 11 Part A as well. So even in this more complicated model, certainly some of the p-values are going to stay, or are going to change, excuse me, but you're going to have similar trends in this more complicated model compared to the one that we looked at earlier. So kind of a big question here, why we call it the Big F test from Handout 10. So a kind of an overarching question is sand type statistically contributing something to my understanding? I know that my R squared went up a little bit, but was that enough of an increase to warrant this more complicated model? Certainly this model is much more complicated than model number 3. And I can do that with the Big F test or the custom test. I need all of the coefficients here for sand type to be set to 0. So I'm going to pick up this coefficient. Which one is that? 0, 1, 2, 3, 4, 5, 6. I'm going to pick up beta 6 and set that equal to 0. I'm going to pick up beta 7 and set that one equal to 0. Beta 8, set that one equal to 0. 9, 10, and 11, all the way down through. Beta 6 through beta 11 all have sand type in it. So if I go back up and look at that big messy model, 6 through 11 here all have sand type in it. So what I would be doing with that big test is just looking at whether or not sand type has any influence. The p-value down here that's e to the minus 21. So that definitely is less than 0.05, and it does have an influence. So the answer to that is yes, sand type is contributing statistically to my understanding of diameter. So this model is more complicated, certainly. I am getting a little bit more R squared. So I'm up to 95% versus 88.5%. So I'm gaining a little bit on the R squared. It will take you certainly more effort to try to explain this model to somebody. I would encourage you to do that, if you need to do that, through these types of plots here. Just picking up different lines and points. Now it's much more complicated than what I've shown here because I have to worry about sand type as well. So maybe you would use open circles and closed circles for the two different sand types. Different marks for the two different sand types and different colors for the different projectile types. Okay, that does it then for Handout 11 Part B, pages 12 through 24. Thank you.